10.
Good afternoon, everyone. Welcome back to this technical session 12 of SESTEC 2020. I request all the participants to switch off their videos, and if you have any query, please send it through chat box to host SESTEC 2020. It is my pleasant duty to introduce the chairperson of this session, Dr. Anil Kumar Babbi. Dr. Babbi is presently serving BRC Tarapur as SOG. He did his PhD from the University of Mumbai and carried out his postdoctoral work at Technical University of Catalonia, Barcelona, Spain. Dr. Babbi has more than 190 publications to his credit, including 20 chapters and 2 patents on non-dispersive membrane technology. He has also served as the consultant to IAEA Vienna for developing technical book volume on application of membrane technologies for liquid radioactive waste processing. Dr. Babbi has been awarded with the prestigious Tarun Datta Memorial Award for his contribution in nuclear and radiochemistry in the year 2005. He is serving as the Secretary IANCAS Tarapur chapter since 2008. I request Dr. Babbi to kindly chair the session, please.
Thank you. Thank you for your kind introduction. So now we are entering in session 15, and we have 2 speakers for this session. First speaker, Professor Diroli, from Enrico Diroli from Italy, and he'll be
Don't do cheating.
well.
Don't do cheating.
Please just share.
Hello?
Hello.
Hello?
Yes.
Babbi sir, you are not audible.
Yeah. Am I audible now?
Yes, now you are audible.
Yeah. So we are entering in session 15, and now we have 2 speakers. The first speaker is Professor Enrico Diroli, and the second professor is Professor José Luis Cortina from Spain. So the first speaker, Professor Enrico Diroli, will speak on subject membrane system for sustainable growth. So I would request host to please introduce the introduction slide for Professor Diroli. Thank you. And Professor Enrico Diroli, he's the emeritus professor at School of Engineering of the University of Calabria and honorary president of European Membrane Society. He is the founding director of the Institute of Membrane Technology, CNR, Italy. And since 2018, he's a distinguished visiting professor at Nanjing Tech University College of Chemical Engineering. And since 2018, he is a guest professor of school at Marine Science and Technology of Harbin Institute of Technology, IPR, China. Since 2012, he is a distinguished adjunct professor at CEDT. He is, in addition to this, he is also currently the chairman of the sections on membrane engineering of EFCE and coordinator of EUDME Doctor School on Membrane Engineering. He is a recipient of various awards and honors. Example, Richard Malling Barrow Prize of the EMS, author of he is the author of more than 940 scientific papers covering in the years various topics in membrane science and engineering, from desalination to membrane reactors to biomedical applications of membrane systems. I am very fortunate to introduce Professor Diroli, and I request Professor Diroli to start his presentation now, please.
Thank you very much. Fabi, it's a great pleasure for me to participate to this conference. Sorry that it's only a virtual presence and not just in Kolkata, but I hope we will have the opportunity of meeting soon again in real normal way. What I'm going to discuss today will be the state of the art of membrane engineering, the contribution membrane engineering is giving to the growth of sustainable industrial world as the one we are living today. But what is more important from my point of view is also to try to show you what has been done, but what is going to be done in the next decades. Membrane engineering is not at steady state. It's not at the end of its development. It's just, in my opinion, at the beginning. If I can have the first slides disappear. Can I have the first slide? What is it?
Sir, your sharing has stopped.
Let me try to share again.
Yes, yes.
Is it okay
Yes,
now?
it is okay, sir.
Everybody is familiar with the fact that we have significant problems today, particularly for the water stress. Water shortage is one of the main issues. However, there are other topics that are a little bit less familiar to the large public. And another second one we have to consider where membrane engineering is going to have a role is the raw materials depletion. As you can see here, in the last 100 years, from 85% to 50% of the minerals on Earth has been the traditional mines have been practically disappearing. And we have now a significant necessity to find a solution to this problem as a necessity to find a solution for the water stress. It's important that these two problems can be correlated. And just in the last few years, a quite significant amount of investment have been offered for trying to solve this kind of situation. Here, for your information, some data. You can see here the case of lithium and uranium examples. In the years, the consumption, the prediction of the consumption for both lithium and uranium is increasing significantly. That is the lithium demand, that is the uranium case. So we are assuming that we will need more and more these two minerals and many others similar. Now, what is important is that if we don't do something to solve the problem of recovery of these minerals in a few years, from 10, 15, 20 years, these minerals will disappear. All of them, everything that we are losing during traditional way of doing, basically at the end are in the ocean. And that's why we can call the ocean a liquid polymetallic ore. Some people are already using this kind of figure. We already are trying to recover some mineral from the water, from the sea, from the lakes, from rivers, but this only for few minerals and traditional one, as potassium, as iodine, sometimes sodium chloride, obviously. Here are some numbers that you can be interested, showing you what is the resource we have on Earth, what has been the production in 2014, for example, and what is more important for us is the concentration of these minerals in the brine of the desalination plants installed already in different locations around Europe. If you look the number, if you don't have time now, but if you read this reference, you will find a situation in which if we take care of the recovery of the mineral from the brine, we can significantly reduce the mineral stress. That means, for example, we can increase the magnesium availability about 100% per year just by extracting the magnesium present in the brine of desalination. And 30% will be for lithium, etc., etc. So the possibility to look not only to the fresh water we are producing in the desalination, but also to solve the brine disposal problem and to minimize this problem in a very positive way, as described here. That means we can use fresh water from the permeate of our membranes, but we can pay a lot of attention for solving the problem of the minerals, paying a lot of attention to the concentrate. Today is called a problem, brine disposal problem, which is growing with the large growing of desalination plant. But in perspective, this brine will be the most important aspect of most part of desalination. Desalination will not be for producing fresh water. It's also fresh water, but mainly will be to extract minerals from the liquid phase, from the sea, from the lakes, from the rivers, etc., etc. In this new strategy, you can see here is for seawater can offer possibility through reverse osmosis and membrane distillation to give you fresh water, but you can have also through the membrane distillation and membrane crystallizer produce tons and tons of minerals, and also using these concentrate brines, we can also transform chemical energy in the difference in chemical potential between salty water and fresh water in electricity. Pressure retarded osmosis, reverse electrodialysis will give us this opportunity. Quite interesting the day that these things will become real. They are not yet real. However, things are changing very, very nicely in the last few years. Keep in mind that for what concerns desalination, already desalination is a very well-established solution, and membranes are dominant in the application. At the start of the century, of this millennium, basically, membranes was relatively covering 20-25% of the total. Today, we are approaching 95% of the desalination plant of the millions of about 100 million cubic meters per day. More than 90%, I think today is 93, 94, are already produced using membrane technology, mainly a reverse osmosis and integrated system. Typical plant here, huge plant that are already have been installed and will be installed. This is in Israel, Zorek. You can see here with a plant of the order of 600,000 cubic meters of water produced daily. Only water at the moment is the final product, but if you make a calculation, an equivalent of about 500,000 tons of salts, of brines, are also produced. And if you start to work on them, that will be a significant contribution to minimize the minerals disappearing that I was mentioning before. Reverse osmosis is a dominant technology. However, we have still problem to be solved. And you can see here, this is a RO plant in California, in San Diego. You can see here that the recovery factor of the fresh water you are producing is of the order 50%. And another problem is what to do with the concentrate. The concentrate, in this case, is just blended with cooling water, and that is a significant cost. Otherwise, you cannot discharge the brine in the land or back in the sea. You are going to destroy the bottom of the sea. So that is a problem, and so it's an additional cost. At the end of the story, the overall cost, for this is a special case, very expensive, but is approaching, you can see here, more than about $2 for a cubic meter. So we have still big results have been reached, but we have to solve the problem. One way to solve the problem is the one I was mentioning before, is just trying to not only looking to the fresh water you are producing, but looking also to the concentrate, to the brine, for minimizing the overall cost. Just to give you an example of what is the expectation, assuming the plant as they are today, as the one Sorek, you can see here that during this year, we have a significant growing of the seawater desalination RO plant in terms of capacity. The plant today, most of them are of the order of these 700,000 cubic meter fresh water, approach about 1 million, and 600,000, 500,000, etc. And this is the new one, in Saudi, 900,000 cubic meters. So big success, but still we have to try to minimize the negative aspect. The recovery factor in all these plants are still of the order of 50%, sometimes less, and the energy and the overall the problem of brine disposal is one of the major problem to be minimized and is a relatively high cost. Keep in mind that big success in desalination, but we have a similar interesting results in other fields. For example, the situation that I was calling dominant of reverse osmosis in desalination, today in the integrated membrane operation in agro-food production, both in terms of concentrate juice or just in a high level of sugar content, is becoming more and more traditional. Less familiar to the large public, no big advertisement on this kind of activity, but apple juice, orange juice, and many other juice today are also produced by combining different reverse osmosis of different membranes operation as ultrafiltration, reverse osmosis, osmotic distillation if you want to approach high level of concentration. So this is not only desalination. When we are talking about membrane distillation, I don't know if you are, I assume most of you are familiar, but it's interesting to notice that on one side, RO is already a dominant technology. But on the other side, there are still significant progress in the last few decades. Here is the case of membrane distillation. Membrane distillation that basically was a scientific curiosity at the end of the past millennium, in the 1990s, starting from the 2000, is increasing exponentially. That means that this process will become not yet applied on large scale, no big industrial understanding utilization, but you can see here what is happening. And together with membrane distillation, you can see what is growing also here, significantly less, is membrane crystallizer, which is nothing more than an advanced utilization of the basic units that and the basic concept of membrane distillation. To give you an example of what is happening, the motivation for this, here's an interesting comparison between the classical thermal system, I mean D, 4,000 cubic meters per hour, that is the unit, and this is the footprint of the same 5,000 cubic meters per hour MD, doing the same kind with the same productivity. And footprint is becoming today a quite significant parameters for in terms of cost, final cost of the water you are producing. It's interesting that the concept I was telling you before is becoming in some country very popular. If you are in Korea, they are talking about the third generation desalination system already, in which the reverse osmosis is already present for producing fresh water, but the concentrate of RO is not more a problem. They are not speaking about brine disposal problem. They're talking about what to do with the concentrate, and they using membrane distillation, pressure retarded osmosis, and recovery, the crystallization, and all the membrane distillation units for producing more water. That means increasing recovery factor, for producing energy, and from recovery of research through the membrane distillation and membrane crystallization system. So the third generation desalination, that was a project that ended 2-3 years ago, is already well accepted for in country as Korea, still at the research stage. You can see here the end of this project in 2018 in a vacuum membrane distillation units of producing about 400 cubic meters per day was the size, has been installed in the south of Korea near Busan, and with interesting results, reduction of the brine discharge about 30% and production of increasing recovery factor and the recovery of minerals. Quite interesting, and this kind of concept is today becoming popular in different countries. Another area of significant success already now that we have to consider are the membrane bioreactors. Membrane bioreactors, you can see here this situation, a traditional municipal wastewater treatment. There are 1, 2, 3, 4, 5, 6, 7, 8 different units working together. If you go to the best available technology that in Europe is considered MBR, you can go, you have basically 1 or 2 units at most instead of 7. And if you look to the parameters, the optimization, all the parameters for the MBR are competitive or significantly better than the one of the traditional biological system still in operation everywhere. It's interesting to see that the trend worldwide for the growing, as we saw before in membrane distillation and in reverse osmosis, same trend. Starting from this century, everything is growing exponentially. And in terms of patents, publication, and large-size plant higher than 100,000 cubic meters per day are growing exponentially all around the world. It's interesting that one country, particularly China, is working significantly with this kind of units. You can see here that they are using MBR not only for municipal normal plant, mainly utilized in Europe, but underground municipal water, industrial water, polluted surface water, they are all treated today with significant success based on MBR and MBR of large size. That means not just small units. That is a fast growing, unexpected at the 20, 30 years ago, but that is the situation. I was mentioning before about food, and you can see the same in food. The market is growing, as I was showing before, based on this integrated membrane operation, exactly something very similar to what has been happening in the salination of seawater, in the treatment with MBR of the traditional municipal water. In the perspective, this does not happen yet on large scale, still project, but assume that what will happen not too far from today, probably that we can develop a new mining industry. And the new mining industry will be mainly devoted to the extraction of mineral from seawater. Exactly as I was showing you before, and that will be one of the major success because the integration of the 3 final goals, energy production, minerals production, and freshwater production will make the industrial sector treating the liquid water quite interesting and quite profitable. Let me just mention shortly that until now we are used to solve water stress looking to the liquid water phase, but there are other possibilities. And today, particularly in Europe, our European Union is sponsoring large project using a membrane condenser. Membrane condenser is not too different from membrane distillation, with a major significant difference. Instead of warming up, instead of using on the feed side liquid water and warming up to create vapor that will go through hydrophobic microporous membrane, you can cool down. You can cool down flue gases. So all the gases present in the atmosphere produced on large scale, in the cooling tower or power station, in the petrochemical industry, etc., you can try to extract the water present by cooling down and transforming, having not evaporation, but condensation. And this water, if you are using hydrophobic microporous membrane, cannot go through, in liquid phase will stay on the feed side, and eventually you can combine this water you are recovering together with contaminants, ammonia and other compounds that are present sometimes in the atmosphere can be recovered and reutilized in a different way. That is not yet applied on large scale, but interesting projects have been sponsored. That is the case in which we have been involved. Matching was the name of this project, working on all the water that is evaporating the cooling tower of the power station, and this one, all this water present here can be just transformed in a liquid phase again and reutilized. And with time, this will not be only for the water recovery, that can be already quite interesting success, but also for other kind of contaminants eventually present in the vapor phase. And you can find already in the literature some of these. This matching project ended a couple of years ago, but interesting hypotheses are still in progress. For example, in the recovery of this water from the nuclear power stations. And there's a lot of problem also with contamination, etc., related to this kind of flue gases that we are losing in the atmosphere. Concentration polarization is less severe, as you know, in membrane distillation and also in membrane condenser, but if you want really to solve at a large scale this problem, temperature polarization has to become familiar to the people working in this area. And temperature polarization, sometimes combined also with concentration polarization, is one of the major issues to be solved. And in solving is not only a question of fluid dynamics and the control of temperature profile or concentration profile, it's also a question of materials. So we have to look to new materials. For example, there is a lot of interest today for this graphene or carbon tubes, etc. Which in principle for membrane distillation are not too attractive. Graphene has the highest thermal conductivity than many other materials. You can see here the traditional celluloacetate of polypropylene or PVDF is a 0.02, 0.1, etc. Graphene is a 5,000. So in terms of control of temperature polarization, forget about the graphene, or is not the most interesting material for sure. You can control, but it's a little bit more expensive. However, if you are looking to this material in membrane condenser, this very high thermal conductivity can help significant in solving the problem. That's why today these membranes related to the graphene or other 2D bidimensional materials are becoming quite interesting, and the selective absorption of water vapor, antifouling properties, hydrophobic nature, and the high thermal conductivity are the parameters making this work quite interesting. You can see here, you can find the literature already data showing how is the possibility to recovery with this membrane condenser, with some kind of membrane. Also, new polymers are used in this case. Amount of water going on normally about 50%, 60% easily. And new polymers are competing with the traditional one. This PVDF is the one that everybody is using today, or polypropylene, but with this ALAR, this ethylene trichlorofluoroethylene system, are just quite similar in performance, more hydrophobic, and a little bit cheaper than other fluoropolymers. So new materials are part also of the studies that has to be carried on. Interesting that you can operate this membrane condenser not only with flue gases, but also with flue gases contaminated with microparticles, which are very often present. Here are some results already published in which you can find this kind of suspension with polystyrene of the order of 0.5 microns, and you can have this retentate with very high concentration of these nanoparticles, but the permeate quite clean, nothing is going through. So this is with in more than 6-hour operation. Basically, you can extract the clean water and separate from a significant contaminated flue gases, not only water and ammonia eventually will decay, but also nanoparticles. And that is the interesting perspective. Looking to what is happening today, living textile are still, it's not, what is it called, technical textile is one of the area of interest. And today you can use textile not only for protecting yourself from the cold temperature or just the humidity, but there is a lot of other possibility just include on changing the structure, the morphology of your textile, including a sensor, realizing textile with a significant level of breathing, and you can capture some particles, release a particle, etc. So technical textile is another area in which the functional textile industrial activities are growing significantly. We are talking now in India. There are in India and China and all this area are significant activities in trying to produce new textile where this thermal function is present, antimicrobial material can be utilized and combined, and the electronic sensor can be installed, etc., etc. This seems to be far away from traditional membrane activities. Is not. The basic aspect, the basic function that you have to understand are traditional for the membrane researcher. It's quite interesting that you can also redesign some of the most polluting and traditional large-scale production that we have in the petrochemical world. The ethylene production, which is a significant problem in terms of pollution and cost, can be also redesigned based on integrated membrane process. And that's, if you can find in literature already, this kind of system where basically all the different, instead of using a cracking of naphtha, using this different kind of biomass or biogas, you can just introduce membrane reactors basically in the production of the ethylene itself, in the separation between the extraction of hydrogen, in the transformation of ethylene in ethanol, etc., etc., without any loss basically of the CO2, where the membrane system are taking care of optimizing this integrated membrane process. If you go in the literature, also here you can find already that oxidative decoupling of methane, methane steam reforming, methanol synthesis, methanol to olefin, etc., are all membrane units present in a not yet real ethylene production, but these is work done together with the engineers who are realizing traditional system, and they are quite interested what can be done now. It's not convenient in terms of cost, etc., but the solution to all the problems related to the CO2 production and different kind of poisoning in the air is related to this kind of hypothesis, in which the experts in ethylene production are not aware, are just not ashamed to put also their name on. Another area where membranes are quite successful is energy production and fuel cell are familiar to all of you, and today more and more when we are talking about electrical car, fuel cell are present. I just like to show you here that it's not only a question of membranes in the traditional fuel cell, but all the fuel cells we are using on board of the car, etc., are mainly based on hydrogen-oxygen reaction or eventually methanol, but the system hydrogen is not present in nature. So we have to produce hydrogen for our fuel cell. It's interesting that in the station where you have hydrogen reservoir or on board of your car where hydrogen is produced, again, membrane systems are present. These are all from methane, for example. You have steam reforming, you have water gas shift, final purification with palladium membranes before arriving to the fuel cell itself. So membranes are not only here in the core of the fuel cell, but are also fundamental in supplying the clean hydrogen necessary to operate in the fuel cell itself. And this more and more is becoming interesting small integrated membrane operation of the size that can stay in the back of your car. Quite interesting and quite promising, and this is growing significantly. And it's interesting that this kind of energy production related to membranes is normally not too well present in the traditional approach. You can see here, this is the global distribution of energy in the different sources in traditional distribution. So you have oil, you have natural gas, coal, nuclear, etc. No one is talking until recently of this energy, blue energy. In our calculation and the literature, you can find already that in principle, the combining these what I was mentioning before with membrane distillation, combining fresh water with salty water across dense membranes, osmotic membranes, we can produce about 17%. You can transform the chemical energy difference I was telling before in electricity with an order of magnitude of 17% theoretical, competing with coal, with oil, for sure, with nuclear, etc. So we have to pay more attention to what is happening here. In Europe, we have been spending some time, and we had companies, Norway, for example, working already and trying to, still too expensive, but shortly, in my personal opinion, related to the increasing cost of energy eventually, but also to the decreasing cost of membrane system, this 17% can have a role much more significant than the one that in the traditional approach is recognized today, 0. No one was suggesting to use this blue energy in real life. And the pressure at osmosis with the system giving. The most interesting new future will be, however, related not only to the development of this new textile or to the development of the fuel cell, etc., but what is happening today in the space engineering. I don't know how many of you are familiar with the fact that if you go on Mars, and here is the typical example, the atmosphere of Mars is basically 95% of CO2. And on Mars, where we will probably land in no more than 1 decade, 1 or 2 decades, 10, 20 years, there is no oil. There is no energy production in the traditional form we are used. There is no coal. There is a lot of CO2. But now CO2 can be an interesting source, and there's a lot of research progress on the traditional membrane technology or in traditional industrial chemistry to transform CO2 in something of interest, for example, in methane. And there is one of the possibility to develop this kind of system where membrane engineering will contribute to the life in the space will be just this one. Now we know also that means CO2 plus hydrogen can give methane, and hydrogen now, we know that on Mars we have water. Water is becoming something that exists. This is ice underwater, just cold water present on the Mars surface, and more we will learn about this. Already today, a lot of activities related to the membrane system are in progress in the space activities. Here you can find in a recent review that we just published called just the membrane technology in space engineering that came out a few weeks ago. You will find a lot of new membranes. This is electrolyte membranes for the reduction of CO2 in this space station. You can find astronauts already in the space station, already working with some new membranes. So this is a SEMSICA investigation. This one was not very successful at the end, but is one of the case that's been studied. And here you can find many other systems of interest already in progress with traditional polymeric membranes, with a system to generate oxygen from CO2 in the Martian atmosphere, etc., etc. Time is running, so I cannot spend too much, but if you want to know more, in this recent review paper, you will find a lot of information of this, including how this fuel cell will operate in space. In the lunar platform, they are already there. It's important to consider that we have been long experienced in the past. If you go in Toulouse in France, where I'm also, by the way, honorary professor, you will find that the Paul Sabatier University is one of the most familiar there. And Paul Sabatier is related to the name of a chemist, Sabatier, who just have been studying the Sabatier process. And Sabatier process is nothing more than CO2 plus hydrogen giving you methane, what we will need on Mars. And that can be something that has been less utilized today on Earth, but will be in the space, will be quite interesting to check and to operate in this way. And in the future, it will happen with 95% that we have there. These are interesting system with support scenario, includes loop system and open system where membranes are doing the job. We're introducing this from the different kind of atmosphere and going through the Sabatier reaction, water electrolysis, etc., we can produce what the energy necessary, the methane necessary. Just to approach the conclusion, around the world, there is a growing attention to what is happening with membrane engineering. And I'd like to mention something that is important to learn, which is happening in China. In China, you can see here, they are growing no more, as in Silicon Valley, as IT, technology, etc., but they are exploring membrane valley. In Nanjing, around the Nanjing Tech University, there are industrial membrane park, already now 60,000 square meter of installation, going to be in 1 or 2 years, 240,000 square meter of installation, 3 times bigger than the one already big now, where company are already in operation, producing at industrial level different kind of membrane system with success. There is already company producing ceramic membrane, zeolite membrane, PDMS composite membrane, gas cleaning membrane, PVDF hollow fiber membrane, all in a large membrane park valley. That's quite interesting. And not only this is near Nanjing, but if you go now in other part of China, the Shandong, last year in 1920, they are creating another membrane science technological research in combination with European researchers. And the first step has been, the operation has been in July 2019. And today in this industrial membrane park, there are already different companies from the United States, from China, etc., in operation. That's quite important, and we have to take care because the competition for utilizing more and more at industrial level membrane technology, not only in the traditional field as desalination, as food, as textile, eventually as pharmaceutical and biomedical application, but in the new field, space engineering, living in the new planet, will be very much interacting with the possibility to realize in the space, not only on Earth, all the success of membrane engineering. Thank you very much for your attention, and sorry for running a little bit. Thank you.
Thank you, Professor De Roli, for your excellent talk and with lot of future perspectives. And perhaps I would like to give a small compliment. That is, we celebrated Waters Day on 22nd. But after looking at your presentation, I think that I felt that we were timely. you have your presentation regarding this water and what you explained about the water and water crisis and exploitations of membrane system for getting the pure water for the humans. So what I mean to say is that we could not have your talk on the 22nd March, but at least we are in the same week. So we have some questions. We have some questions, and see first. I'll see the chat box. So the first question is, did you see the short term for mineral recovery process from our brines in Europe or in general in the world more than the project described in Korea? Very interesting presentation. I mean, so that is, he has asked about that question about the RO brines.
Very short time to expect. In Europe, no, we are working a lot today on the brine disposal. We are not more interested in producing fresh water because the system works. Research have been done excellent work in the past years. Now we are looking what to do upstream our membranes. That means on the feed. And there will be much more interest in the feed extraction. In Europe, you can find 3 large multinational projects sponsored by the European Union just devoted to the recovery of, I don't know, strontium, uranium, lithium, rubidium, barium, etc., from the brines of the desalination plants already running, and looking more and more to the future. Which other plants will be installed? I'll show you all the data. There are huge plants, 100,000 producing millions of cubic meters of fresh water. For 1 million cubic meter of fresh water, you are producing around 1 million tons of minerals on the other side of the membrane. These 1 million tons of minerals is much more valuable than the millions of fresh water, except for the people who need water. But in terms of value, there is this water will be given for free in the future, and the real profit will be on the minerals. In the United States, there are trillions of dollars research projects for the extraction of rare earths from the sea. Trillions of dollars. That means, and that most part of this money will be also related to membrane operation, totally or in part. So all around the world, starting from the last project I showed you from Korea, by the way, Europe was #1. I was director of a project in the 2015 called Medina, where for the first time we introduced the concept of the recovery, increasing recovery factor by treating with membrane distillation and membrane crystallizer the brine of the seawater. So this is becoming, initially was one project, relatively small amount of money, few $1 million. Today there are trillions of millions of dollars devoted to the recovery of minerals from the sea and from lakes. If you go to China, there is a lot of lakes very rich in minerals, and they have a specific project for the recovery of minerals from lakes, salty lakes. So the answer is yes, there will be significant attention, not tomorrow, today, already in progress, and more, assuming that the results of this research in progress will be successful, as the one in Korea.
Yes, my next question is that the graphene-based membranes are being widely used nowadays, but what is the degree of fouling of these membranes when used in seawater, when used for seawater? So graphene membranes,
yes.
What is the...
Well, at my knowledge, there are no graphene membranes really tested on significant scale for desalination for seawater. So difficult to give an answer. However, I don't expect any significant, first of all, people are still looking what they have to use, graphene or graphene oxide, which is not the same story. Both of them, they are different from graphene oxide and graphene. Also, one is more hydrophobic, graphene, one is less hydrophilic, graphene oxide. So if you use graphene oxide, you expect less fouling problem, more with graphene. However, my suggestion is don't worry too much about graphene, also because it's expensive and difficult to realize. Most part of the graphene paper that are being published, well, if you make the test was not graphene, was graphite, No, most part they buy as graphene, but in real life is graphite. There are new materials, a lot of 2D strange. So we are publishing today. We just submitted papers where we are using not graphene, but we are using some 2D material as a telluride, selenide. Bismuth telluride is the salt that we've been using, and these membranes filled with no, with bismuth telluride, and there are many of these cases that you can investigate are much more interesting, also considering the fouling problem than just graphene. So wait a few weeks, hopefully, or a few or months, depending from the reviewers, and you will find papers discussing not about graphene, but some other 2D materials that in principle can be competitive with graphene itself. And these are still 2D materials, but not graphene. Typical example, the one we are publishing, but you can have hundreds of this kind new salts, totally unknown until years ago, as telluride, selenide, etc., etc.
Okay, so one question from me, and this with regard to the process intensification, which factor do you feel that is very important with regard to the hollow fiber contactors when we apply for a metal separation or this kind of application?
You know, I am in love with process intensification strategy because we are assuming that membrane engineering is today one of the best answer to the process intensification strategy. And there are three examples. One, I show one slide in terms of footprint. Now, people normally were not very involved in footprint. Today, footprint is becoming quite important problem on Earth, as I was showing, but also moving in the space. Membranes systems can satisfy very nicely problem of energy consumption, of compact system and footprint, no vibration, etc., for space application and Earth application. So there is not one parameter, but all the set of remote control, automatization, footprint are all interesting non-traditional parameters that in which membranes are having leadership. And this one can become very important in the process intensification strategy, assuming that energy, quality of the product, etc., have been already solved in the past years. But the new aspect, from my point of view, is remote control, level of automatization possible, footprint, etc. These are becoming quite important in the logic of process intensification. And for the space, particularly.
So many thanks, Professor Doroli, for your excellent presentation. And we really thank you for enlightening us regarding the current scenario of the membrane technology as well as the future perspectives. So thank you very much. Thank you very much,
Thank
Professor
you.
Doroli.
My pleasure. Thank you.
So now we are moving to the next speaker, Professor Luis Cortina from yeah. He is a professor chemical engineering at Barcelona Tech, UPC, and senior research director at Water Technology Center. And he has a research expertise, separation processes in chemical environment and mining engineering, development and integrations of water technologies and process for drinking water production, urban and industrial waste water treatment, real-time water quality monitoring, development of reactive materials for in-situ groundwater remediation technologies, including honors, awards, and fellowships. He has got an exchange award for Society of Chemicals Industry from SCI, and member of several agencies such as the Spanish National Agency on Chemical Technology and Environmental Technology Perspective, Science and Technology Spanish Agency, and Chemical and Environmental Technology Panel. He is a member board for the Barcelona Multi-Skill Science and Technology Research Center, and he has got more than 200 publications and 250 communications on scientific meetings and book chapters. Very happy to introduce you, Professor Jose Luis Cortina. I request you now to present your talk.
Okay, thanks, Anil, for your kind introduction. Let's go into, I just load my presentation. I hope everything's going to, can find. Is everything okay, Anil? Could you see my presentation?
Yeah.
Okay.
Be able to listen. You have to share the slides now.
Okay. It's a really pleasure this invitation from this conference. It's a really amusing and impressive conference on separation processes, and it's a good opportunity to capture all the progress that you are developing in India, especially. And it's also a pleasure, yes, being after Professor Drioli. Yes, I'm going to provide let's say probably one of the samples that was mentioning that is related to the integration of membrane, liquid membrane conductors as a part of a process treatment where the objective is to recover ammonium from urban wastewater. This process or this concept is related to the moving that is occurring in wastewater treatment facilities that for many decades they were just built for reliability on removal pollution from wastewater, and as a whole these facilities they were, let's say, energy consumers. And probably in the last decade it was let's say a big effort to identify if these installations could be, let's say, energy positive, or at least they were not able to, or not requiring energy to develop these treatment stages. And this is traduced in the modification or in the development of new treatments that additionally to the fact that the objective was to recover carbon to produce energy. In parallel, it has been introduced that also there is one possibility to produce from this carbon source, for example, polymers, or to recover nutrients and to recover water for reuse. This altogether has been introduced. Sorry?
Excuse me, sir. It's not shared. Your slide is not shared.
Okay. And why not? Okay. Sorry for that.
Yeah, it's now sharing.
Okay. Sorry for that. I'm sorry because I was asking, you were saying, okay, let's start. Sorry. This is my first slide. Thanks. Sorry for that. I was just trying to explain that we are now in the stage of wastewater treatment facilities are moving from their initial conception of working on reliability for removal of the organic or the pollution load that is in the water. And as a consequence, there were installations that they need energy to be operated. And then in the way of reduction of the energy consumption, just taking benefit of the organic load that, or the content on carbon that are present in wastewater, everything has been modified. That's a new concept for such facilities that they are now understood that they are going to be like resource recovery facilities. And then you will find in the literature that people is talking about that wastewater treatment facilities are going to be biofactories or biorefineries, or depending of the company, they identify as resource recovery facilities. Then to understand why, for example, it's going to be possible to recover nutrients, as is the case that I'm going to show later, let's go into start to understand what is the first action that should be taken. The first action that should be taken is in the way to make this facility, let's say, energy autosufficiently. We need to modify the classical conventional activated sludge that we have here in this scheme, where after a primary treatment, we move to a secondary treatment where by using microorganisms, we mineralize part of the carbon that is lost as a CO2, and then the biomass is sent in for the anaerobic digestion stage when we are able to recover biogas. But this is not enough to be energy sufficient, and then we need to increase the amount of carbon that is sent to this stage. This has been introduced in the development of a new concept. It's identified as two stages or A and B stage. Then we remove this biological reactor, and then yes, we have a first stage where with a very, very short retention time, we try to move or to send the highest amount of COD that we have in the water to the anaerobic digestion to increase the production of biogas. This, when you are accounting for this scenario, your energy self-sufficiency in terms of electrical or electricity requirements move from the old 20 to 35% by the use of the biogas, close to, I think, even a little higher than 60%. And also we have a second benefit, but we have a carbon footprint reduction, because most of the carbon that is lost when it was converted to CO2 now is still converted to biomethane. Sorry. Then, but in this new scenario, what happens is that we are going to accumulate in our mainstream a large amount of nitrogen, and then we need to provide a solution for this nitrogen. Nitrogen has been considered for many decades like a real dramatic anthropogenic problem, because it was related to the discharge of untreated waters with large amount of nitrogen and phosphorus were responsible by the eutrophication process. And then most of the effort was devoted to remove nitrogen, and the most efficient way is to be converted to nitrogen. But we are now facing a second, let's say, sustainability challenge. That is the growth of the population is increasing the need for fertilizers. And then according to the last estimation, is the Haber-Bosch process that is used to produce ammonia is accounting a little bit more than 2% of the total primary world energy consumption that in the world. Then there are now many initiatives or many problems yes, to reduce this effect or this impact of the Haber-Bosch process. And then one possibility could be to recover the nitrogen from the wastewater treatment plants. Then if we just come back to what is going to be our new wastewater treatment scheme, that is simplified here in a very, very simple way. And yes, I'm showing you the mass balance for the COD and for the nitrogen. Let's go into take now only attention only into the nitrogen. And let's go into take as a reference value 100. Imagine that we are just, we have as an input value of the total nitrogen 100. Here we have the carbon redirection technology, where we try to maximize the amount of carbon that is going to be sent for anaerobic digestion. But now let's go into follow what happens to the nitrogen. Is a large amount of nitrogen is going to be just not removed from the water. And then even if we take into account the amount of nitrogen that will be just collected, sorry, from the anaerobic digestion, we have more than 90% over this value is going to be present in the water. And then we could have two options working in the old mode, just thinking on nitrogen removal, and then we will probably lose 65% of this total amount in relation to the initial one. But if we go to the recovery options, we have the possibility to recover, let's say, close to 90% of the total nitrogen that is arriving to a wastewater treatment facility. Then the question is, there are many possibilities. Carbon has been typical, or sorry, nitrogen has been typically recovered by using air stripping or even vacuum technologies, but our decision was a little bit different. Yes, we put some key performance indication for the selection of the nitrogen recovery technology. And then we were initially having some requirements or some constraints. If we are going to recover nitrogen from the let's say mainstream of this new process, values of total nitrogen or total ammonia could be something between 40 to 100 milligrams per liter. And we want to produce a byproduct that is going to have, let's say, a high quality, because we identify that this product or this byproduct could be used directly as a fertilizer for agricultural applications. And then we need to avoid the presence of pollutants. And a second objective was just to produce a concentration of ammonium nitrate or ammonium phosphate that are typically used by the agronomic applications, but then the target value of the content of our stream should be something that the content of nitrogen should be reached the typical expected values for liquid fertilizer, as is something between at least above 10% in content of nitrogen. Then the selection was to use liquid membrane contactors, but liquid membrane contactor using hollow fibers they are having let's say a very important requirement that the quality of your feed that is entered into the liquid membrane contactor it should be, let's say, is having two main concerns: is the absence or the minimum amount of particulated solids on your stream, and secondly, to reduce the amount of COD or dissolved organic matter in the water. Then, for that reason, we decide to integrate the recovery stage by using the liquid membrane contactor with a pre-treatment stage using an ion exchange technology and selecting as the most suitable ion exchanger for ammonium removal using natural zeolite. We were using a natural clean octinolite. And then the system is working in this way. We have the water for the mainstream, let's say with values with 40 to 100 milligrams per liter. Then you treat this water with ion with some zeolites, and then you concentrate your ammonium in the bed, and then you regenerate the ammonium. You could be just working in the regeneration with a sodium chloride solution, but as because of the fundamentals of the liquid membrane contactors, we decide to use a sodium hydroxide solution to regenerate very efficiently the zeolite stage, and then we are getting let's say a very basic solution. Let's say sometimes probably pH is going to be around 12, even a little bit higher than 12, and then this is fed to the liquid membrane contactors, and then in a countercurrent way we use a solution of a strong acid, as for example nitric or phosphoric, or if you want you could use a mixture of both. And then you will get your concentrated solution of the ammonium nitrate or ammonium phosphate, depending the acidic solution that you are using. And a very important parameter in this system that is going to define the economical viability of this process is that the sodium hydroxide rich in ammonia that is entered into the membrane contactors should be just reused for the regeneration stage, because the cost of the sodium hydroxide is really high. Okay, then we decide to test the system. We make the proof of concept in let's say working with synthetic solutions, using microporous hydrophobic membranes of polypropylene. The system is working quite very good. It's removing very efficiently. We have two examples from one solution just after a concentration stage with zeolites, or let's say of 4.5 grams per liter or 1.5 grams per liter. And then if we keep the performance of the system, only ammonia is transported through the pores of the membranes to the acidic side. Okay, but we have a second requirement, that we need to have a very concentrated stream, as concentrated as we could, to reach the fertilizer requirements needs for being applied in agriculture. And then we set up a system when we were working with, let's say, the smallest volume that we have for the stripping tank, and the largest one for the ammonia stream. And the system is operating in a, let's say here, in a recirculation mode. We will see that we were testing if one stage is enough, or probably in some cases more than one stage is going to be needed. We were using this polypropylene modules of 1.4 square meters from 3M. And we have a system where, depending on the strong acid use, we have a control pH where we should be operating, let's say, something between pH 2 to 3 when you are operating with nitric acid, and you should be operating between 6 to 7 to avoid the formation of some ammonium phosphates that are precipitating in more acidic conditions. Okay, let's go into show some examples. The operations here, for example, with a solution containing nitric in the green symbols, or we have using phosphoric acid using one stage or two stages, and a second one just using a mixture of nitric and phosphoric if you want to produce a mixture of ammonium nitrate and ammonium phosphate. Here, the most important thing, apart from the capacity of the fiber to reduce the values, remember that we have a threshold that is very important. That is the solution, that is the rich solution in ammonia should be recirculated to the ions, to the zeolites column, and then we set a threshold that the minimum value of ammonia in the stream after the contactor should be something a little bit below, like 200 ppm. And then, for example, here in this case with nitric acid in one stage, we were close to reach this value, but when we incorporate a second stage, we were reaching values below of 200s, and then in that way the sodium hydroxide with this small amount of ammonia will be used in the regeneration stage of the zeolites column. Okay, this is in relation to the system being able to operate and to recover ammonia, and then just to reach levels below 200 milligrams per liter. But a second very important problem is that the system should operate and should produce a really rich liquid fertilizer, and we should avoid that in our receiving stream. We are not having any problems or any other component from the feed side that is transported through the membrane. And one of the main problems that typically you are facing when working with liquid membranes contactor is pore wetting. Then here you have the evolution, and we were just following the evolution of all dissolved species, inorganic ones, main anions that we have in the feed. Like, for example, we have other cations like potassium and magnesium and calcium that they were kept constant all along the filtration stage. This is an indication that your system is not suffering from pore wetting and only ammonia is transported. we were also following the values of anions that are present on the feed solution. And here you have the evolution, for example, of the phosphate or the ammonia in the stripping side or circuit, when only ammonia is transported and we could see neither cations or neither anions are present in solution. Then we were able to operate the system, avoiding the issues of pore wetting. A second part of the study was devoted to identify the operation modes. We could say that even there are many industrial applications for liquid gas or gas to liquid using these hollow fiber membrane contactors. There are very few cases where or industrial scale cases of the application of liquid membrane contactor, especially for this case of ammonia removal. And then there were many doubts that the module module provided, they were not giving answer to us, and they were not sure. And then we were just checking if the module should be in horizontal or in vertical position, or what should be if the feed should be just put into the shell, into the lumen. And then we were evaluating all these performance indicators in terms of operation modes, and we were just using the quality of the fertilizer that is produced, and yes, we were also following the recovery factor and also the evolution of the mass transfer coefficient along this filtration stage. And here you have the values for some experiments with phosphoric acid. Here we have some experiments with nitric acid, and then finally, I think we identify that modules are probably better working or operating in a vertical mode, and then having the feed with the ammonia and the sodium hydroxide solution just to be sent to the shell, and just running with the acidic stream through the lumen. Okay. This is in relation to the operation mode. Also, we were really interested on the influence that is having the cold transport of water through the membrane pores. As we are just trying to get a very concentrated liquid fertilizers, this is having let's say an associated problem that the salinity or the ionic strength of the acidic stream is going to be increasing along the filtration stage. And then we are going to promote that the difference in the vapor pressure for water between both sides is going to be increasing. And then as you could see here, initially at the starting points water is transported from the ammonia sodium hydroxide solution to the stripping phase, but as much as the concentration of the liquid fertilizer is growing, then at the end we have that we are going to be transporting water from the feed to the stripping phase. No, I said originally in a wrong way. Okay, then this is something that is fighting against us, because at the same time that we are transporting ammonia from the feed to the stripping phase, as much as the difference in the salinity increases, also we are increasing the water transport. This is not so critical, because here you have the number for the fluxes that ammonia is having, let's say, at least 2 orders of magnitude higher values for fluxes that the water that you are transporting. And finally, the last effort, because there is no way to keep or to monitor if any pore wetting event is occurring, yes, we decide to install as a monitoring tool just to follow the presence, especially of organic compounds that are also going to be, let's say, affecting the quality of the fertilizer. we were able to follow anions and cations in solutions, but also the stream that is fed to the liquid contactor is having some presence or some values of COD. And then we were using neither UV or two-dimensional fluorescence to follow the quality of the fertilizer that is produced. And here you have, this is the feed just coming from the zeolite column. And here we have the typical presence of some organic compounds that are typically present in wastewater. And here we have on the bottom part the same spectra just for the stream that is produced of the ammonium phosphate or the ammonium nitrate, where we could see that we are not able to detect the presence of any organic. Then I think that we believe that operating and keeping control that your operation mode is just being so safe to assure that you are not going to have poor wetting, then the quality of your product that is going to be produced probably will fulfill all the regulations that especially we have in Europe in relation to the fact that you are just trying to put in the market one material that is produced from one resource that originally was present or part of a waste. Okay. Then, in relation to the water transport problem, because we face that to such extent we have some limit for not being able to get one fertilizer with a content of nitrogen probably more than 10%. Yes, we test the possibility of increasing the concentration of the liquid fertilizer if after the liquid membrane contactor we install a second concentration stage using electrodialysis. Electrodialysis has been successfully applied for many decades in Japan for concentration of seawater to produce table salt. Then yes, we integrate. Here we have the values for two initial concentrations of ammonia just sent into the liquid membrane contactor. We have a very good recovery ratios. We reach, let's say, quite suitable contents for the nitrogen and the phosphate values, and then just we move then to a second stage where those ammonium nitrate solution and ammonium phosphate solution were sent to a EV stack. We were using two different type of cationic and anionic membranes. We were using one cationic and anionic membrane from Fujifilm and a second one from PCSIL. Independently of the initial concentration of nitrogen on the fertilizer, we were able to reach concentration factors that were just moving probably between 1.5 to 4, sorry, to 2. Okay, then as a maximum, by using electrodialysis, you will be able to increase the concentration of your liquid fertilizer by a factor of 2. Here we have the electrical consumption in kilowatts hour per kilograms of salt produced, and here the Faraday yield. The Faraday yield was, not say, moving between, let's say, in some cases 30% up to 90%, but as is happening in the liquid membrane contactors, also in the electrodialysis stage, as you are increasing the difference on the concentration, and you are concentrating your feed on the liquid fertilizers. Also, you face the same problem that you modify the water activity, and then you have just transport of water through the membrane due to this difference on osmotic pressure. Okay, but it's a possibility or a final possibility if you have not been able to reach the requirements in terms of concentration of the liquid fertilizer. Okay, then now we are in the stage that we have we are able to produce all this liquid fertilizer, but we have some requirements from the EU on the way that this liquid fertilizer should be used in a real scenario using field scale trials, where you use with different crops, and then you need to analyze is there any, let's say, presence of pollutants or contaminants in the crops after they grow. Okay, and this is something that now is in the stage, because this will be used, let's say, to overcome the regulation on the use of such fertilizer, because they are coming from an originally waste origin. Then my second, then as a summary, still there is not totally completed. I think at laboratory scale or laboratory pilot scale, I think there are very good perspectives. But now is a second stage that everything should be just evaluated in a industrial pilot scale. We probably need to make to improve or to work on the reduction of the water transport, and then we could just a little bit play in with the temperature between both sides to reduce the difference in the vapor pressure. We need to validate the control of the performance on pore wetting, and then to analyze the membrane for fouling events. And then we will integrate these online monitoring systems by using UV and two-dimensional fluorescence to provide a very good quality indicators in relation to the presence of priority pollutants. And we need to still working on increase the reuse of the caustic solution, just leaving the liquid membrane contactor to be reused for in the ion exchange stage, because I think even the initial calculation we should reach that at least more than 100 cycles with the same sodium hydroxide solution is requested. And then we have two initiatives, is to start working a new polymer chemistry from a new trend of liquid membrane contactors. It's called ligase. They are produced by 4-methylpentane-1. And finally, we have some initial attempts to evaluate, to compare the performance of the spiral one modules that are used for membrane distillation examples. Okay, this is in relation to the work done when we were treating the mainstream with low contents of ammonia. But in the time that I have, if we come back to our scheme, when we have the nitrogen mass balance, here remember that we have been just trying to check if we recover the ammonium from the streams that are generated here. But there is one second possibility, is just to recover the ammonium from the stream that is generated in the anaerobic digestion. Okay, this is let's say a small, or in comparison with the mainstream, is a lower flow rate, and additionally a more concentrated solutions. Typically we move that we are going to face streams that are having, let's say, from over 0.6 grams per liter up to probably 1.3, 1.4 grams per liter of ammonia. The conditions of our requirements were the same. And then it was built, this project is a demonstration project that is run in a wastewater treatment facility in the south of Spain. The project is devoted not only to recover ammonium salts, it's also devoted to recover also the phosphate that is present in the water. And some of the units were built at full scale. For example, the elutriation stage to recover phosphate, and the recovery of phosphorus by crystallization, and the recovery of ammonium by liquid membrane contactors was developed a pilot scale. And in the last years of the project, again, all these fertilizers that are being produced along the project are going to be validated in real scenarios, just checking their use and performance with different type of crops. Okay, if we just look one small scheme, remember that before we were working with mainstreams. Now we are going to be working here with the streams that are generated in the anaerobic digestion stage. Then these streams are sent first to a first stage when phosphorus is going to be recovered as a strobite. And then the stream after the phosphorus removal stage is sent to a UF stage when we are going to remove the organic matter or dissolved organic matter and the suspended solids present, and again to be sent to a zeolite, and then in parallel in the next stage the liquid membrane contactors. Here you have the scheme of the system. We decide to put two liquid membrane contactors in series. We were using these modules from 3M of each one, like with 33 square meters, the extra flow D007. And here you have some pictures of the pilots at the industrial site. Here is the pilot for the UF and the ion exchange stage, and here is the pilot for the liquid membrane contactors. And this is some work that is under development along this year, and then I have some preliminary results, but we have not time to show you today. What we have been working in parallel is to integrate the knowledge that we developed previously to develop a one-dimensional model to be used as a projection tool, a design projection tool. Then we integrate different mechanisms that we have identified. The transport of ammonia through the micropores, and also we have introduced in a similar way transport of water that we have also through the micropores. Then we have integrated all the mass balance in the different parts of the system, in the feed side, in the stripped side, and then we follow the changes on the feed side, and also all the changes due to the volume of acid that we are adding to produce the liquid fertilizer. And here are some results. For example, some examples. One example for where the shell side was the feed, and the lumen was having the phosphoric acid solution. You have that we are predicting quite very good the profiles of the evolution of the concentration of the ammonium in the stripping phase, and the decrease in the feed side, and also the variation of the volumes due to the water transport. A different example with a different configuration. Here the lumen was for the feed, and the shell side was phosphoric acid. Also we are getting very good prediction of the performance. We are also matching the transport of water through the pores. As we mentioned originally, the water is transported from the stripping to the feed side, and then we have these negative values for the water transport, and as the concentration in the stripping phases increases, then we are starting getting that water is transported from the feed side to the stripping side. And also we were able to determine both all the permeability parameters for both ammonia and water, and then we are now having a good design projection tool for to be used in the deployment of this technology the case of ammonium removal from wastewater. Then what is just to finalize, this second part with the side streams is a part of the project. It's still going. We hope to finalize the pilot campaign with this 1 cubic meter per hour pilot. And then we are facing originally some problems with the treatment of the water that is coming from the crystallizers, and the UF stage is providing some problems. And then now we are evaluating some alternative low-cost pretreatments to overcome these limitations in the ultrafiltration stage. We are developing or moving from the one dimension to two-dimensional model to describe the transport of ammonia and water. And finally, we are also going to get two small pilots, one using spiral wound modules from Solar Spring, and we hope to also to check is a new technology that has been developed for this company in the Netherlands, CBAP, that is using, let's say, low-cost membrane modules for evaporating, or for, I don't know, it's difficult to say what is typically occurring, but at the end is to transport ammonia through a polymeric material, and using a very low cost modules where you could replace as it was as a consumable. Okay, and then to fight the problems that we are facing, that the COD levels at the total inorganic contents that typically you are facing in the side streams are much higher than those that you are getting on the mainstreams. Then just to thank all the funding bodies that have been supporting these projects, and to Martin Ulrich from 3M for the contribution of the projects, and to all of you for this kind attention. Thanks.
Thank you, Professor Jose Luis Cortina. Perhaps I think is a very enlightening talk, and then we could see some kind of pilot plant experience of your hollow fiber contactor work, and is really interesting. And also that is, I appreciate that you discuss all the problems, also what you have faced and how you resolve those problems. So perhaps I think then I have got two questions from audience. So I will take one by one. The first question is that, do you expect any change in performance if the materials of hollow fiber membrane is changed from polypropylene to PVDF or ECDA or PTFE?
Okay, this is a very good question, because I could say that in the fact is that the market for liquid membrane contactor, at least the market that we are available in Europe, is mainly in the hands of 3M. That even 3M got the Membrana or the Hodge-Celanese, let's say, all companies. They are not interested. They are only commercializing the polypropylene modules. But I think just moving to PVDF or PTFE are going to improve or to reduce the water transport. And I could say that water transport has been for us, let's say, a large challenge, because when you are going to a pore wetting event, to remove the water from the micropores is quite difficult. And sometimes because you have some protocols or some guidance from the company, with let's say some drying stages with air, with hot air, but at the end in some cases you are not able to recover your module, and then the price of one module, it could be 2,000, 3,000 euros, and then you know, is for wetting events is going to be catastrophic for this technology if this is not controlled. And then PVDF and PTFE, for sure, they are going to, let's say, to have less tendency to go to pore wetting. But from the information that we got from especially 3M, they are not seeing at short term that they are going to produce these modules with other material than polypropylene. Then now we are testing this second 4-methyl pentane material that is produced originally by a company in Japan, Separel, and Separel just decided to make a joint venture with DuPont. And DuPont now is going to commercialize this new material for let's say, liquid treatment or liquid separations, okay? And the initial trials that we have performed with this new polymer, I think is having much better performance in terms of kinetics. I think the process is much more, let's say, efficient in time basis, and still we are not having the let's say, the long performance with pore wetting. Okay,
Yes.
but it seems promising.
Yeah. What I understand that in your case, I think the problem is the hydrophobicity of the membrane.
Yeah.
So in case, for example, there are some suppliers, if you customize or if you explain your problems, I think they are also making some kind of special membrane for you, which could be a more hydrophobic than what you are using now.
Yeah.
There are more hydrophobic membranes now available in the market. Maybe, for example, I will tell you, there is a new technology. These people are just putting some kind of coating on the membrane, and they try to increase the hydrophobicity by that coating. So this kind of membranes are also have come in market. So you need to more explore about this kind of material where your hydrophobicity can be increased. If once your hydrophobicity can be increased, then your water transport can be reduced. Once your water transport can be reduced, your fertilizer quality automatically will it will be graded. I think you understand what I want to say.
Yeah, no, it's totally right. But we are curious because when you are trying to get large modules, because typically for all these pilot scales, we are just moving to modules that are, let's say, around 50 to 60 square meters of area per module. And we were not able to find many providers. Are those providers in India or where are those companies providing?
Here also the dominating is by 3M. So here also the 3M. The market is by 3M. Now there are some local vendors available, but in Europe and United States, you have a better this kind of things. So if you talk to them, customize your I mean, your requirements, so they can make for you more hydrophobic membrane. This is available. And the second question is there any tolerance in terms of TDS or total organic contents of the wastewater for this? What you process your wastewater to be processed?
This is a very good question, because we just follow the recommendations from the membrane providers. Okay, you could not have, let's say, if you are just looking to the recommendation guides, they will say 0 of COD and 0 of total suspended solids. No. Because they want to, let's say, not going to you into let's say, warranty issues. But for that reason, we decide to put in place a UF system to reduce the amount of suspended solids. Okay, to put a UF unit is a very, very expensive, let's say, option, or is going to increase your total cost. And I could say that there is one running a full-scale application in Germany in a wastewater treatment plant, where instead of using UF, they are installed like let's say a system when they have like some coagulation stage, and just follow it by two stages using, let's say, some filters and dual filters. But at the end, you need to reduce and to put inside your modules the small amount of suspended solids that you could, because otherwise
I agree. I
you
agree
will
with you.
lose modules.
Yeah, I agree with you. And with this, so once again, I thank you for your excellent presentation, and well, hope that is your presentation could be very useful for our young engineers.
Okay, thanks a lot, and thanks for the congratulations for the conference.
Thank you, Dr. Pabbi, for chairing this session. We have come to the end of technical session 12. We will have a short break now, and participants are requested to reassemble for the next technical session at 4:40 p.m. IST. Thank you.
एक मिनट बात करना चाह रहा है।
A small announcement for the participant. I'll request participant Priyanka Shah, Kakuli Priyam Goswami, Preeti and Krunal Mistry kindly contact the LOC SESTEC. Again, Priyanka Shah, Kakuli Priyam Goswami, Preeti and Krunal Mistry kindly contact the LOC SESTEC. Through chat, or you can call. Dr. Sriram, can you hear
Sir.
us?
Yes, I can. Can you hear me?
I can hear you. Your slide is also seeing, but I am seeing your back end slide.
That means you're seeing the notes, is it?
Yeah, I'm seeing the note. I think you have to share the other. You go to the display setting and choose the second option.
Oh
In
boy.
the top, there is a
Okay,
display setting in the top. Middle.
Displays. Okay. Display setting on the top.
Click that, and
My mouse is for some reason not moving to. Let me just check what I can do. Oh boy. Yeah. Oh, this is strange. Just 1 minute. There's something really strange going on. Hold on. So Are you able to still hear me? Hello?
I'm able to hear you.
But you're not able to see my presentation, is it?
No, I'm not able. I'm able to see your presentation. It is in the normal format where you can do the editing. It's not in the
Yes.
slideshow. It's not in the
Okay.
slideshow mode.
So let me go to my presentation.
Go to F5. F5. Yeah, that's perfect.
So are you able to see my presentation now, or are you able to see the notes page also?
No, again, it gone to your note page, or that is your PPT. You have to slideshow. Yes.
So does it now show all the background notes?
And now it is still moving. It's still showing the note.
Oh,
I can
and you said I should display settings and
display setting. The next option. No. Second option. Duplicate slideshow.
Is it better now?
Yeah, just click it. Yeah, this is the option. It is now visible now properly. Proper show is there.
Okay.
Okay, so temporarily I'm moving you from presenter. I'll just load your biodata and then introduce you. Then you can again do this sharing again.
Okay. Thank you.
Okay, thank you.